In this part of the Computational Intelligence course, we are going to examine the vanishing selective pressure problem in evolutionary algorithms. And then we are going to cover the methods for adapting the fitness function in order to overcome the problem. Problem of the absolute height of the fitness values with respect to the variation. Or this is called also problem of vanishing selective pressure. Consider these two functions, g and f. Maximizing of f, which is a function from omega source space to real values, this is the fitness function, is equivalent to maximizing of f from omega source space to real values, this is the fitness function, is equivalent to maximization of g, this is again from omega to real values, with value gx is fx plus a constant. C is selected from the real numbers. In the case, the value of C is much more larger than the superior value of the fitness value of the x values. X are representing solutions in the source space. We are considering the superior value, the largest value. And here, for example, for this f function in the source space, this is the maximum value. And C is much more larger than that value. If this is the case, then G relative of an individual in the population will be equal to 1 divided by the population size. So if there are n individuals, each individual will have almost equal chance. So this means that too small selective pressure. Remember the definition of the relative fitness value. This is the fitness of the individual divided by the summation of the fitnesses of all individuals in the population. The problem is perhaps grounded on the evolutionary algorithm itself. It increases tangentially the average fitness of the individuals. For example, consider the early generations here and suppose that in the search space, the fitness function has values like that, and some individuals are selected randomly in the source space. Then, in the later generations, due to the proportionate selection, we will have more individuals around the local maxima of the fitness function. So higher selective pressure at the beginning due to random fitness values. The fitness values are random here. Later, we will have smaller selective pressure. However, the inverse way is preferred. We are desiring low selective pressure in the beginning, but high selective pressure in the later generations. So, a solution is scaling of the fitness. Different way of scaling may be used. For example, in linear dynamical scaling, the fitness value is adapted such that the original fitness value of the individual is multiplied by alpha, and then from that, this value is subtracted. Here we are considering all the individuals in the population, and we are considering the fitness value of those individuals at time t, at iteration t, and we are taking the minimum value of the fitnesses in the population. We are subtracting that value from the fitness value multiplied by alpha. So we are finding the adapted fitness value of that individual. Instead of minimum of the population, minimum of the last k generations can be used, and usually this alpha is greater than 1. In row scaling, we are considering the standard deviation of the fitnesses, and the standard deviation of the population is multiplied by beta, and this is subtracted from the mean value of the fitnesses of the population. These are calculated at iteration t, and this difference is subtracted from the fitness of the individual, and standard deviation adapted scaled fitness value is calculated in this way. Here the problem is that also for the linear dynamical scaling, choice of the parameter alpha and beta. Consider variation coefficient of the fitness function. Consider the whole search space, and there calculate the standard deviation, and also calculate the mean value, and variation coefficient is standard deviation divided by the mean value. At that time, we can define variation coefficient as the standard deviation of the population divided by the mean value of the fitness values of the population. Empirical discovery shows that if variation coefficient is around 0.1, this yields good ratio of exploration and exploitation. If V is not close to 0.1, then the adaptation of the fitness value, for example by scaling, may be used. V can be estimated instead of calculating it. In practical calculations of V, replace of search space, use the individuals in the population. So instead of omega, we are going to use the population, and we are calculating what is the variation coefficient. Hence, approximation of V by selection intensity at time t with that population is used. In each generation, calculate selection intensity for generation at time t and adapt F accordingly. For example, row scaling, standard deviation scaling with beta equal to 1 divided by the optimal selection intensity, which is 0.1, can be used. Consider different functions. Here each one is obtained by shifting the original one. For this one, selection intensity is 0.2. This is too high, so it may result in premature convergence. For this one, mean is higher, but the standard deviation is the same because the shape of the function is the same. Then the calculated selection intensity is much lower, around 0.05. This is too small selection intensity, so we have vanishing selective pressure. This one is resulting in premature convergence. For this one, it is too small, so results in vanishing selective pressure. And this is corresponding to appropriate selection intensity. It is 0.1. In another way, for the adoption of the fitness function, determine the relative fitness not directly from the fitness values of the individuals, but from a function gx, which is exponential the fitness value of the individual divided by a constant k multiplied by t. T is time-dependent temperature. T controls selective pressure. K is normalizing constant. Temperature decreases, for example, linearly considering the predefined maximum number of generations. And then as T decreases, whichever has larger fitness, then that individual becomes dominant in the population.